Hi. Well, thanks for the invitation, and I'm very happy to give a talk here. Now, when I received an email from the organizers about giving a keynote speech on the third day of the workshop here, I had to ask them back, what do I know about the symbolic structure nor the symbolic, I don't know, AI? I do know a bit about the neural networks and deep learning, but the other side, the symbolic side, I had absolutely no idea. So I was a bit anxious about it, but one of the organizers, David, actually assured me that it's going to be fun to just give a talk at this workshop and talk with the people. So I decided to go ahead with it. And since then, I've been giving a lot of thoughts on what is the thing that I want to share at this workshop that is titled Symbolic and Neural Learning. And I decided to talk about a very, very latest work that was done together with my PhD student Ethan Perez and my collaborators at Facebook AI Research, Dao Kila. And then this is nothing that is too exciting, nor too groundbreaking, but this was a work where we did spend quite a lot of time, let's say a month, trying to figure out what is the thing that has excited so many people, including myself, about this fuchsia learning with a large-scale language model that was sparked by the recent work on GPT-3 from OpenAI. So let's see what I can tell you, and then see if there's anything that you might get out of this. So first thing I wanted to talk about is what fuchsia learning is, or at least what I thought fuchsia learning was as a machine learning researcher. In fuchsia learning, our goal is to come up with this so-called fuchsia learner F that is going to take as input a set of few examples and outputs a model or a primary configuration of a new model that can handle a completely new example. So you can imagine this as a learning algorithm that works very well with only a small number of examples. Of course, just like any other algorithms that we know, this fuchsia learner itself comes together with some hyperparameters. So if we write the whole thing in one line, this fuchsia learner is going to take as the input n many examples, where n is often very small, and then outputs the parameters of this learner or the model G that can now classify or make a prediction given a new example x prime. One of the, let's just look at some of the representative examples of this fuchsia learning algorithms. So one such thing is a so-called prototypical network by Snell et al. From 2017. In prototypical network, this prototypical network architecture is going to look into many different sets of the few examples, and then trying to figure out what is the right way to embed a new set of examples, these few examples, so that we can use a dot product, very simple operator, to figure out to which class this new example x prime belongs. So it returns a prototype vectors given a new set of few examples. That's the reason why it's called prototypical network. Another example is a model agnostic meta-learning, or in short, MAML, proposed by Finn et al. In 2018. Almost exactly same as a prototypical network, but instead of returning the prototypical or the prototype vectors against which a new example x prime is compared, it actually outputs the initialization for the SGD to take few steps using a very small number of the examples in the test time. Now again, where does this initialization come from? MAML learns this initialization from looking at many different sets of the fuchsia examples. What this actually tells us is that fuchsia learning is really nothing but very much equivalent to supervised learning. And what do I mean by that? Let's imagine what we need when we do a supervised learning. We need a training set of examples, we need a validation set of examples, we need a test set of examples, and then what we end up with is some kind of regression or the classification model. Now, let's try to map all those things into fuchsia learning. First, training set. Instead of training set of examples, we are going to have a training set of fuchsia training sets. So we have a set of sets. And each of these fuchsia training sets consists of the few IID examples. Now, similarly with the validation set, we have a set of fuchsia validation sets. And now you can guess, what we're going to have with the test set is that we're going to have a set of few shot test sets over which we're going to report how well this few shot learner works. And then what we do is that we're going to use this training set validation set in order to estimate both the parameters as well as the hyperparameters of this few shot learner. So we're getting so many different levels of the parameters, but in reality, if we zoom out just a bit, we are just doing supervised learning when we talk about few shot learning. So what do? We use a training set of, or the set of training few shot data sets in order to find a good hyperparameter or the parameters of this few shot learner. Now, of course, this process has a hyperparameter, which I have used lambda to denote here. Now, in order to pick that lambda, that is a hyperparameter or the meta hyperparameters, we use this validation set of few shot data sets. And then once that is all done, we're going to use this test set of the few shot data sets or the few shot data sets in order to tell how well this few shot learner is going to work in the sense of the generalization. So really, other than the fact that we have two different levels of the parameters as well as hyperparameters, it's really just supervised learning. Of course, what does that mean? What it tells us is that there is no such thing as a free lunch. Is that even in the case of the few shot learning, we need to have some information, that is that a lot of data of the data sets in order to run the model selection and find the correct hyperparameters or parameters of this few shot learner. So we really need some information or the extra signal that allows us to do model selection as well as learning in the case of few shot learning. And this is really, really true for not only few shot learning, but transfer learning, multilingual learning, you name it, anything that where we use multiple sets of data sets or the multiple tasks, we need this kind of meta information that often comes in the form of the multiple similar but not same tasks or the data sets. And it's just very, very inevitable because of the free parameters feed as hyperparameters of this few shot learner itself. So what that means is that we have to be a bit careful in a sense that in order to avoid any kind of information leakage. So if you look at the prototypical network as an example, to get the parameters of this embedder, so the embedder that's going to take as the input this few shot example, the few training examples, and produces these prototype vectors. In order to get the parameters of this embedder, we should only use this training, validation, and test sets of few shot data sets. We should never use the actual examples of the test time few shot examples. Similar thing with MAML as well. In order to get the initial parameters for this few shot SGD to work with, we should only use a separate sets of few shot data sets, training, validation, and test sets of the few shot data sets. And we should never use the actual few shot examples that are going to be used in the test time or the deployment time in order to figure out what this initialization is. And what that implies is that that includes the hyperparameters that are involved or the hyperparameters that define the algorithm MAML itself. So what that means is that it's really, really tricky to do proper evaluation with few shot learning. We must have collected or synthesized a set of data sets. And then we all know that just creating one data set is a pain in the ass, and somehow we need to have a set of multiple data sets. And then we have to be extremely careful about the information leakage across training, validation, test sets of data sets. Now to address or to work with this tricky evaluation setups, people have started to propose some of the better benchmark suites for few shot learning as well as the transfer learning. In 2018, there was a new data set or the new concept of the benchmark called the metadata set, where they propose a standardized benchmark for the few shot learning and computer vision. And in WMT, they started to have this unsupervised and low resource track ever since, if I remember correctly, 2018 or 19. And then they actually have defined all these splits very, very carefully so as to properly evaluate multilingual transfer for few as well as a zero-shot learning in machine translation. So there are efforts, but we need more efforts in this way of building up a more proper benchmark suites for evaluating future learning, or transfer learning, or whatever the more or less a meta learning setup. So this has been my understanding of what future learning is. But then last year, there was this big bombshell from OpenAI talking about GPT-3 and how language models are future learners. I took this this quote from the GPT-3 paper, which actually received the best paper award in Europe last year. Let's just read it out together. We show that scaling of language models greatly improves task-agnostic future performance. GPT-3 is applied without any gradient updates or fine-tuning, with task and future demonstrations specified purely via text interaction with the model. This is just amazing. This is essentially the kind of dream that everyone had. And in their paper, they describe what it means for future learning to happen, or even zero-shot learning to happen with a language model. In the case of zero-shot learning, we're going to describe what the task is in natural language, and then give them the input, or give the language model what the input that this future learner language model needs to predict the label of. In the case of the one-shot, all the same thing, but we're going to provide also the example. So the one particular training example, or the one example per label, again as a natural language, in addition to the natural language text description to this language model. Now you can guess what the future is going to be. You're going to have multiple examples like that. This is really, really awesome, I gotta say. Let's try to map this to what we've looked at in terms of the future learning now. So, and then we often refer to this whole procedure as prompt engineering. So we have GPT-3, or a very well-trained large-scale language model, in the middle. And then we have this new set of few examples that we can use in order to define a problem. And then we have new example that we want our future learner based on language model, or the language model based future learner, to make prediction of. Then here comes us. So here is the prompt engineer who's going to look at all these training examples. So the very few training examples and a new test example that we want our GPT-3 based future learner to answer. And then we engineer this prompt. So we need to engineer the description of the task. We need to engineer how we present these few examples. And then we need to engineer how to tell, or what are the options from which this GPT-3 based future learner could answer from. And then once everything goes into GPT-3, GPT-3 is going to read this test description, presented examples, and the options, and produce the single final hidden state. Let's call it theta. And then the theta is going to be compared using a dot product against the possible target class tokens, again, engineered by the human, like us, and then it's going to give us the answer. This is pretty cool. This is actually really interesting, because essentially we are assuming that this language model GPT-3 knows natural language, just like we do, so that all we need to do is just figure out how we talk with this GPT-3. And then all we need to do is we just ask it to answer this very difficult question. That's very cool, except it turned out that there are actually a lot of hyperparameters in this GPT-3 based future learner. We need to figure out how to describe the task. We need to figure out how to present examples. We need to figure out what is the right target token set to use. It turned out we even need to figure out what is the right number of training examples to present. Then it kind of goes on and on and on. But then this part is same as before. The memo needed its own hyperparameters to be used for the gradient descent, or the gradient descent by gradient descent. Prototypical network also needed the hyperparameters of the gradient descent there as well. So it's all the same thing. So it really hasn't changed much. However, what's different from the conventional notion of future learning in this case is that there is no notion of the training validation future tasks. If you read the GPT-3 paper, just like I did actually yesterday, you notice that there is no notion of the training validation sets of future data sets. which I thought at least were necessary in order for us to get a good future learner eventually. So this is very interesting, both interesting and also a bit, this is the kind of thing that makes me a bit skeptical. So that's why, we decided to delve deeper into it. But again, let me just say that I am and I was and I continue to be very excited by this possibility of interacting with this gigantic neural network used purely using text and then being able to force or entice it to do something that I want it to do. This is extremely cool. It's just that what is the right way to tell, or how do I know what I need to tell GPT-3 to do what I want it to do? And then this prompt engineering has become a big thing overnight, essentially. GPT-3 paper was published online less than a year ago. And then, since then, it has received the best paper award in Europe. And then this year, and then there's been tons of papers that have been published online as well as in some of the conferences, receiving sometimes best short paper award, outstanding long paper award, outstanding short paper award, and so on and so on. So we have actually ample, let's say, existing studies to build up our case. So the very first thing we started to do is to figure out how all these papers have chosen their prompts. So how did they actually engineer these amazing prompts? Maybe, there was no effort needed. Maybe any natural way in which we can put it, maybe GPT-3 just understands it perfectly. Maybe not. We decided to go into each of the paper and then trying to figure out what the answer is. So when we look at the Brown et al. 2020, that is the GPT-3 paper that received the New York's 2020 Best Paper Award, they actually said that they used the development set to choose various hyperparameters, including the number of the examples to present to GPT-3. Wait, hold on, development set. What is this development set? Presumably it's just a validation set of examples. But then what is a validation set? Validation set is a set of examples that are already annotated. All right, it's a bit confusing in the sense that we are doing future learning, and then the whole point was to have a very few examples, labeled examples, and somehow they have been using a development set of labeled examples. Interesting. So we went to the next paper, Tam and Mel et al. From 2021. They actually very explicitly say that they assume access to a full development set to choose the best masking ratio and checkpoint model. Okay, so future learning, but they still assume the full access to full development set of the labeled examples. And you go into yet another paper, let's say Redfold and Kim et al. From 2021, they repeatedly queried performance of full validation sets to guide the development. And then if you go into their code, they actually even mentioned that they use the entire training set in order to find a good prompts. Okay, this is getting a bit further and further away from the future learning. And another paper, Kuhn and Eisner 2021, which just received the best short paper award from the NACO 2021, which happened 2 weeks before this workshop, or 2 or 3 weeks before this workshop, and is happening as I record this video. They also test with a model that performed best on the dev set. Okay. And then we actually continued on, and then we looked at 2 other outstanding papers from NACO, and then they also used the hyperparameters based on previous work, which often use the development set or the validation set, and based on practical considerations, whatever that means. So it looks like how they have been finding prompts has not been based on only few training examples that have been given, but using a very large set of labeled examples that is called validation set. In other words, it's not really truly few shot. Rather, what they have is that they have a future learner that takes as input a very many labeled examples. Some of them are labeled as few training examples, and the rest are labeled as a validation examples, but still they are a set of labeled examples. And this fuchsia learner, which we probably shouldn't call fuchsia learner anymore, is going to output the parameters of this learner that's going to classify a new example. And then the hyperparameters are largely gone because these hyperparameters are going to be selected using these large labeled validation examples. So what that means is that it turned out that the prompt engineering that was put forward and got me as well as the whole community extremely excited about was not really for fuchsia learning, because it turned out that we actually don't use only a few examples, but we use a very large examples. Very large set of validation examples. It's just that there's a very lousy way to use a large labeled validation examples, but nevertheless, it's a labeled examples. So in some sense, it looked like it was fuchsia, but it wasn't really a fuchsia to start with. But still, again, I want to just emphasize that I'm still very excited about this. And I was excited about this possibility already quite some time ago. In 2014, before we wrote this attention-based neural machine translation paper in Montreal, we actually had the very first glimpse at the power of neural language models for question answering, as well as solving a lot of challenging problems. What we tested back then was to give some unknowns, so out of vocabulary token, Korea is a friend of the United States, as the input to this English to French translation system we built. And then we asked this translation system to we prevented this translation system from outputting the out of vocabulary, the unknown tokens. And how we translated was to translate it as a South Korea is a friend of the United States. It's very interesting. So I replaced friend with an enemy and then tried it again. And then it actually translated this unknown Korea into North Korea. What it meant was that this translation system we trained actually had a lot of knowledge of the word and was able to actually answer some of the questions according to its own knowledge of the word. So yes, I'm extremely excited about this possibility of using language model as a fuchsia learner, multitask learner, or the knowledge base, which I believe that the Graham is going to talk about after this talk. And I want to be excited. I want to continue to be excited by this power of language model. I just wanted to check whether this is the case, because existing studies took one step toward making me even more excited, but there are a few things that we had to check in order to be even more excited about this possibility of future learning with language models. So we decided to run some experiments, a bit thorough, perhaps a bit boring, but thorough experimentation. So the setup is that we're really, really going to assume that there are only few examples for both hyperparameter selection as well as training. And then when we say hyperparameter selection, we include everything, including prompt engineering. And when we say training, training is really nothing but just a forward pass through a language model such as GPT-3. We use the OpenAI's API. We only learned recently that the model behind the API access may not exactly be the GPT-3 that was described in their paper, although we believe that they must be more or less compatible or comparable to each other. And for evaluation, we test how well this model does on a reasonably large held out set that was not used at all for any kind of hyperparameter selection, including prompt engineering nor training. So we really try to make sure that this is really truly few-shot learning setup. And then for evaluation, we not only look at the mean or the average accuracy, but also the variance across the different sets, let's say, subsets of the training set and so on. So then what do we need in order to run these experiments? The first thing is that we need to have a hyperparameter selector that's going to take as an input a very few labeled examples and then get us the hyperparameters of this fuchsia learner. And then we need to have the actual fuchsia learner that's going to take as the input the combination of the hyperparameters and this small number of the few training examples in order to output the actual model. And then we need a predictor that's going to take as the input the one example that needs to be classified, and these parameters that were outputted by this fuchsia learner. And then what we're going to do is we're going to see how well this predictor works across the test examples. But again, these test examples are not the ones that are used for fuchsia learner nor for hyperparameter selector, or by the fuchsia learner nor the hyperparameter selector. So this is slightly different from some of the recent studies, which have instead reported the loss or the risk where the hyperparameter selector H use not only these few examples, but also a very large development or validation set. So what that means is that generally this risk or the loss that was reported by the recent studies were actually underestimating the loss or overestimating the generalization accuracy than this true fuchsia learning setup that we're going to test. So how do we actually select the hyperparameters when we have only a small number of examples? We just go back to a very classical, let's say, machine learning practices. One, we use a k-fold cross-validation. And the second one, we try the minimum description length, which is relatively straightforward to compute, in particular because learning is nothing but just a forward pass through this large-scale language model. And then, we did test a few other things based on a various intuition and the justification. It turned out that none of those actually works that differently from either the k-fold cross-validation or minimum description length. So one of the difficult part about the prompt engineering is that the prompt engineering is inherently a very difficult problem. The space of prompts is combinatorial. It's just like a natural language. It says the space of prompts is identical to the space of natural language. It's gigantic. And then, of course, because prompts are just natural language, their length vary from one to another, which makes it really tricky to do any kind of optimization. And also, we have to even decide what is the right way to put the examples or to present the examples as well, those few examples. It's so difficult. This space is very complicated. So we are going to rely on a set of predefined prompts coming out of the previous studies, as well as some of the automated methods. And then what that means is that we are still going to underestimate the loss or overestimate the accuracy compared to the truly doing the combinatorial search or some kind of approximate search on the entire prompt space. Because all these predefined prompts from the earlier studies were somewhat carefully chosen by people who were looking at the development set as well as the test set accuracies. But nevertheless, it just makes sense in a sense that if our belief is that the GPT-3 or these large-scale language models do understand natural language, then we would always start with some reasonable set of the predefined prompts and then try to use whatever the hyperparameter selector that we decided to use to pick one out of this predefined set of prompts only. So what are some of the questions that we want to answer in order to tell whether this GPT-3 or the large-scale language model-based fuchsia learning is really the thing that should make us as excited as the original paper actually did last year? First, we want to tell whether we can identify a good, if not the best prompt, using only a few training examples rather than a very large validation examples. That is, do the prompts selected using either the cross-validation or MDL match the prompts selected by the large validation set? So that's the first question we wanted to answer. And the second question we wanted to answer was, if we use a prompt selected by either cross-validation or MDL, can we actually do fuchsia learning as well as the fuchsia learning with a prompt selected using the large-scale validation set? Well, not even that. We're actually going to see if we can do better than randomly selected prompt. It sounds like a pretty low bar, but no one has actually tested it. So we wanted to double check that the prompt engineering actually is a thing instead of just using a random prompt. Now, the third question we wanted to ask was, what is this gap in the accuracy between the Fuchsia learning with the validation set selected prompt versus, let's say, this Fuchsia training set selected prompts. We expect that the loss is going to be lower when we use a larger validation system, because we can get a better, we overestimate them, but we wanted to just double check the whole thing. We tested largely, we did actually, we used multiple data sets, but our main experiment was done using the data set called Llama by Petronio from 2019. It's a benchmark for retrieving facts from a language model. We use a very particular split, and then we use a subset that has removed all those helpful names. And the prompts, we use the manually curated prompts from the Llama, the original paper, and also some of the automatic paraphrases from Alpaca. And then I believe that Graham is going to tell you much more about this Alpaca. So first, can we identify the best prompt? Given only a few examples without any validation example. So that's the emphasis here, is that can we do so with only a few examples without any validation examples? It turned out that it's actually pretty difficult. We could only recover the best prompt or predict the best prompt less than 30% of time almost always. And then in fact, it got more and more difficult when the underlying language model got larger. When we use the full GPT-3 175 billion model, assuming that is what OpenAI is using to serve their clients via their API, the chance of predicting or recovering the best prompt using either CV or MDL was around 20% or so. And the funny thing is that these accuracies were relatively insensitive to the number of training examples we use for Fuchsia learning. And then we tried it going from 5 all the way to 40. Of course, it's not all the way, like 40 is small, but when we think about the Fuchsia learning, and in particular in this kind of context of the language model, due to the limitation on the length and everything, 40 is actually pretty much the maximum we can go. And then what we saw is that using more examples did not actually help us find the best prompt that was identified using a very large validation set. So that's not a great news, but let's continue with the second question. Can we do better than a randomly chosen prompt? Again, given only a few examples without any validation example. It turned out that, the answer is barely so, and this is barely so with a very high variance. So we observed a less than 20% relative improvements, and then the variance was so high. So instead, what we looked at is that what is the chance, or how often do we expect a selected prompt to result in a worse accuracy than randomly selected prompt? It turned out that it's about 60% of time that this accuracy using the selected prompt was lower than the average accuracy over the randomly selected prompt. So this is actually a pretty damning, let's say, observation, is that if you wanted to deploy this system with the prompt engineering as a key aspect or the key component, then it just says that it's just as good as not doing the prompt engineering or whatnot. And then this is not only for Llama dataset. We actually made a similar observation across multiple datasets such as RT, WIC, as well as CV. What that means is that it suggests that there has to be a way to choose a prompt a priori without looking at these only few examples, but by incorporating other information such as the other tasks or the sets of the other, let's say, Fuchsia tasks. Okay, so far the answers are not really, let's say, positive. But let's move on to the third question, which is probably the most important thing. That is that how much do we lose by being truly Fuchsia learning? It turned out that there is a clear gap, and then indeed the accuracy that we would get by choosing prompts or the hyperparameters based on a large validation set is the upper bound to the actual generalization accuracy that we can get when we use only a few examples, even for selecting hyperparameters as well as prompts. And then sadly so in terms of accuracy as well. When we really use only few examples, we do no better than choosing random prompts. But of course, there is not only all gloomy. In fact, it turned out that generally so, when we have a larger underlying language model, we do get somewhat better accuracy. What that means is that the hyperparameter selection or the prompt engineering is important, but generally so, the accuracy goes up as we get a better and better underlying model. So this was the one thing that we could actually get as a positive, let's say, observation out of all these experimentations. Of course, it turned out that it's not only prompt engineering. Of course, prompt engineering is difficult because prompt space is combinatorial and whatnot, but there are many other hyperparameters that are almost as difficult as prompt engineering. And then we have used the algorithm called AdaPet in order to fine-tune the whole language model in order to solve the new problem based on a few examples. And what we saw was that it's the same thing. When we really use only few examples to do the hyperparameter search, the accuracies do significantly lag behind the optimistic accuracy that people have so far reported using a very large validation set of labeled examples. So in other words, in future learning, no hyperparameter is easy to find or trivial to find. So this whole project actually started with excitement. As I mentioned earlier, I've been excited by this whole idea of using language model or the translation model, the more or less same thing, as a way to encode the knowledge of the word and then retrieve those, let's say, knowledge by querying it using language model. I've been excited by this possibility ever since 2014 or so. So I was very excited. And Ethan, as well as now, all of us were extremely excited about this GPT-3. However, a bit more careful experimentation and a bit more careful, let's say, setup of the problem itself made us make some somber realizations. The main message is that the future learning is still challenging, even with GPT-3, 4, 5, I don't know, whatever the GPT-X is going to be. Because we just don't have enough examples. When we have only a few examples, it's just not easy to do anything. There aren't enough signal that we can use, not to mention to learn a new model, but even to find a good hyperparameter configuration. And then this hyperparameter configuration actually corresponds exactly to finding a learning algorithm, because they actually define that or determine the algorithm. And then if you think about it, there are only a small number of examples. How are we supposed to search for this gigantic space of algorithms? So it just cannot, future learning just cannot be easy. And the second realization, perhaps it's not a realization, this is how we actually, the whole community used to define the future learning to be, is that we need something extra. We need something extra to find a good hyperparameter configuration, i.e. find a good future learning algorithm. So meta learning, transfer learning, in those, let's say, contexts, we've been using other similar tasks. And perhaps we can view the prompt engineering as yet another machine learning problem of inference. But I don't know what is the right direction to go. But this is the realization that we made, is that we need something extra. Unfortunately, however good this language model is, there is no free lunch. We need some extra information in order to know how to tell this language model to do what we want it to do. But I gotta say, this is still extremely exciting because it actually bridges symbolic structure and neural learning. So we're getting back to the name of this workshop now, is that we now have a neural net-based execution engine that is called GPT-3, or the large-scale language model. And then what we're doing is to try to figure out how to write this instruction in a symbolic way. So using a symbolic structure to write the instruction that is being given to this neural execution engine that's going to execute this symbolic instruction and then give us the answer. So this is a very exciting way to bridge the symbolic AI and more of the parallel distributed processing based AI. So again, I'm very excited about this. This is extreme opportunity that we have as a field, because this seems to tell us what is the potentially the right way to bridge symbolic and distributed representations in the way of symbolic instruction executed by our neural execution engine. And then this perspective actually gives us a lot of different ways or the avenues to pursue. First, example-based meta-learning. So if we have a bunch of the different tasks and then be able to induce this symbolic instruction out of it that's going to be used by this language model-based neural execution engine, you can view this as a program induction. So what have we learned from this program induction? Can we actually use some of the techniques from there in order to use these language models as actual future learner will? And if you think about the description-based meta-learning, because there was always a text description that is in natural language, what that means that actually corresponds to program synthesis. Now, given a description, can you come up with a symbolic instruction that's going to be given to a language model that will execute what this task should do? And that's a program synthesis. What can we learn from this whole, let's say, large era, the discipline of the program synthesis? So it's very, very exciting. And then perhaps this idea of language models as future learner will truly withstand the test of time, as indicated by the Best Paper Awards Committee of NeurIPS 2020. So let me just conclude it by saying that although we have made a lot of negative observations in this work, we are all very excited about this new potential opportunity that is opened up by GPT-3 and the large-scale language models. And then it just tells us that we have to be careful in setting up the problem. And then, given the carefully set up problem, we have to be more exploratory and then adventurous in terms of trying to look into what are other aspects or the other disciplines under machine learning and AI that can be used in order for us to maximally benefit from this new paradigm. And hopefully we'll be able to talk about this throughout the workshop, this week. Thank you very much. And if you have any questions, please do talk to me, I believe over Zoom, or of course you can always drop me an email or talk to me on Twitter. Let's say Twitter. And I'll try my best to answer. Thank you very much.